So we know how to find an inverse of any function. You switch x and y and you solve for y, okay? And I'll give you an example of that right there. We're going to be doing inverses of logarithms and also the inverses of exponential growth or decay functions. And all you need is a little trick, the magic trick that allows you to get rid of logs or to get rid of exponent situations. You could magically add log base anything you want to both sides of your equation, or you could raise both sides of an equation to become the powers of the base of your choice. Okay? So right here, if I tell you to find the inverse, well, you're going to switch the x and the y. And that's what I do right here. The x is out here, the y is now up as an exponent. Now, not only do we switch x and y, but we also solve for y. So how am I going to get this y down from an exponent to become a regular y? I'm going to have to apply a logarithm, log base 6 to be more specific. If you apply a log base 6, you don't have to write it, okay? Just watch. If you apply log base 6 to both sides, the log base 6 of 6 will cancel out and the y comes down and it becomes a regular y. That's exactly what I explained right here. And that's exactly what I'm showing right here. I apply log base 6, apply log base 6. The log base 6 of 6, that eliminates, and your y comes down like magic. And you end up with y equals log base 6 of x. Okay? And if I wanted to find the inverse function of y equals log base 6 of x, I could switch x and y, solve for y, and it would take me back to the original y equals 6 to the power of x. If you don't believe me, watch this. Let me actually do that. That's y equals log base 6 of x. Y equals log base 6 of x. So if I want to find the inverse, I would switch x and y. So I'd have x equals log base 6 of y. And then I would have to solve for y. But you see, y is inside the logarithm base 6. And I don't want the log base 6. I just want a regular y. So to undo the log base 6, I want to take this entire side and raise it to be the power of base 6. And what I do to one side, I must do to the other. Raise this to be the power of base 6. So what do I have here? I have 6 to the x equals 6 to the log base 6 of y. That way, the 6 to the log base 6 cancels out, the y comes down, and 6 to the x stays. And that is the inverse of y equals log base 6 of x. I just went forward and backwards, right? I took the inverse of y equals 6 to the x. I got y equals log base 6 of x, and then I took the inverse of that to get back to that. Do we understand what I just did?
No.
No? You switch x and y and solve for y. Again, what I'm demonstrating here is that you could magically add log base 6 of anything to both sides of your equation, or you could raise both sides of your equation to be the powers of the base of your choice. With those two things, you could eliminate logs, you could bring down exponents, right? If you want to bring down an exponent, you're going to apply a log base, whatever you need. If you want to eliminate a log, you're going to raise it to be the power of the base of whatever you need. Let's go over some more examples here. Example 2, it says find the inverse of y equals ln of x plus 3. First of all, this ln, that's called the natural log. And we have two special kind of logs. They're the common log and the natural log. The common log is base 10. So if you ever do have a base 10, you don't actually have to write log base 10. You could just write log and you automatically assume it's base 10. If you have log base e, you don't actually have to write log base e. You just write ln. ln is really a log base e. Do we understand that? Okay. So if I wanted to find the inverse of this function, y equals ln of x plus 3, I will first switch x and y. And here it is. And now I want to solve for y, but you see y is inside this log base e. Okay, y is inside this log base e. So I don't want this log base e. So whenever I have any type of log and I want to get rid of the log, I'm going to raise it to be the powers of the base of my choice. So because this is log base e, I'm going to raise the entire right side to be the power of base e. And what I do to one side, I do to the other side. I want to raise this x to be the power of base e. So I really have, let me repeat right here, e to the x equals e to the ln of y plus 3. Now, why would I do that? Because e to the ln, that's really e to the log base e, and that cancels out, and my y plus 3 comes down. Does that make sense? And I actually show my work up here. You could just go up to the top part of this right column. When you apply e to the base e, when you raise both sides to be the powers of base e, well, right here it cancels out. The y plus 3 comes down. Equal sign comes down. E to the x comes down. And now let's solve for y by subtracting 3, and there's your answer. Y equals e to the x minus 3, which is an exponential growth function, if you think about that, because e is greater than 1. So we're going to be able to apply logarithms to get rid of exponent situations, and we're also going to be able to raise logarithms to become exponents to get rid of logarithms. Does that make sense? It's all going back to this underlined magic trick that we got here. You could magically add a log base, whatever you want, to both sides, or you could raise both sides of your equation to be the powers of the base of your choice. So on number 1, let's find the inverse here. How do we find the inverse? We switch x and y, put an x here equals log base 7 of y. And now I need to solve for y. But you see, y is inside log base 7. I don't want log base 7. So how am I going to get rid of a log base 7? Raise it all to be the powers of the base of your choice. Now, what's the base that you're going to choose? 7. Right? So you're going to take this whole side and raise it to be the power of base 7. Likewise, you're going to take this x and raise it to be the power of base 7. So you really have 7 to the x equals 7 to the log base 7 of y. Why did I do that? Because 7 to the log base 7, that eliminates. And the y magically comes down to a regular y. So y equals 7 to the x. Or y equals 7 to the x. That looks nicer with the y on the left side. But that's how we do the inverse of a logarithm, right? Switch x and y and solve for y by raising it to be the power of the base of our choice. Now, here's another shortcut that we have. Whenever you have a logarithmic function with no h or k, it's super easy to find this inverse, because all you have to do is pretend that the log's not there, and you could actually see it right there. Y equals 7 to the power of x. Y equals 7 to the power of x. That's like a super shortcut magic trick right there. Okay? To find the inverse of a logarithmic function when you do not have an h or k. If you had a plus 3 in parentheses and a minus 5 on the outside of the parentheses, you cannot do that trick, right? But if it's a regular logarithmic function with no h or k, you could simply cover up log, and that will be right there your inverse function. Y equals 7 to the x power. Y equals 7 to the x power. Of course, the actual math that's going on when you find the inverse is that you switch your y and your x, you switch it, and then you solve by raising it or applying logs. Let's take a look at number 2 right here. Let's switch x and y. And I hope everybody's following along. We have x equals 8 to the y power. So after you switch x and y, you solve for y. So what are we going to do there? We need to get that y that's in the exponent position. I need it to come down as a regular y. I don't want it as an exponent. So how do you undo an exponent? Applying a log, right? So what kind of log will get rid of this base 8? A log base 8. So put log base 8 right there. And what you do to one side, do to the other. Log base 8 over here. And of course, this log base 8 of 8, that cancels out. The y comes down nice and beautiful. And this is your answer right there, log base 8 of x. So let's write it the nice way with the y on the left and the log base 8 of x on the right. See, it's not that bad. Let's take a look at number 3. We have y equals e to the x plus 3. By the way, just for funsies here, is this an exponential growth or decay function? Growth. Why? Because the e is really the irrational decimal value, 2.7 something something, and it continues forever. Kind of like pi, 2 point something, it's definitely greater than 1, so it is a growth. So from left to right, it should grow. What about this? Is this an h or a k value? H. It's an h, okay. Just wanted to review that. Anyways, let's go back to finding the inverse. So let's switch x and y, put an x there, equals e to the y plus 3. Now, I need to solve for y, but y is in an exponent position. So, Michelle, how could I get that y down from the exponent on top of that base e? Okay, how do you undo an exponent situation with a log, right? So how are you going to get this exponent y, actually this whole exponent y plus 3, how am I going to get it down to be a regular y plus 3? By getting rid of this base e. And how are you going to get rid of the base e, Alexandra? We're going to get rid of this base e by applying what to both sides? Log base e. Now, what is log base e really? It's really an ln, right? I mean, you could, if you wanted to, write log base e, but don't do that because there's a shortcut for writing log base e. The shortcut is just writing the letters ln. That means natural log. That's really a log base e. What you do to one side, you do to the other side, ln of x. So the ln of e, that eliminates. The y plus 3 comes down. It's no longer an exponent. It's now a regular y plus 3 on the right side of the equal sign. And on the left side, we have ln of x. Again, ln is really just log base e. Now we need to get y by itself, subtract 3, subtract 3. So your final answer is y equals ln of x minus 3. Now let me ask you this right here. On this logarithmic function, is this an h shift or a k shift? It's a k shift. It's a number that's all by itself at the end. Now some people would say, well, wait a minute, it's being subtracted from x. No, it's not, right? Right here we had the ln of x as one item, and then we subtracted 3 separately. So that's the ln of x, and that minus 3 is the k value separate. It's not part of the log base e. Keep that in mind because number 4, we'll see something completely different. Number 4, let's find the inverse by switching x and y. We're going to have x equals 2 to the y minus 3 separately right there. Now, I need that y to come down. So, Bella, how do I get that y to come down from the exponent?
You don't use razor.
Okay, check this out, guys. If I have a times 3 and I want to get rid of a times 3, I'm going to do the inverse, which is divide by 3. If I have a plus 5, I want to get rid of it by subtracting 5, right? The inverse operation, right? What is the inverse of an exponent? A logarithm. What's the inverse of a logarithm? An exponent. So if I have this y as an exponent, I need to get rid of that exponent by applying a log. But even before that, y is up here on the right side of the equal sign. Even before bringing this down to a regular y, there's something that I could easily get rid of, that minus 3, right? So let's get rid of that minus 3 first by adding 3. And what you do to one side, do to the other side. So what we have now is the equation x plus 3 equals 2 to the y power. There's my new equation. X plus 3 equals 2 to the y power. And now let's get that y to come down from the exponent position. Ariana, how are we going to get that y to come down? Log base 2. Thank you so much. And what you do to one side, you do to the other side. Now check this out. I'm going to do the log base 2 to this entire side. You see how this is actually an x plus 3? It's a binomial. I need to put that in parentheses when I apply a log base 2 on this side. Okay? If I didn't put the parentheses, it would seem like if I'm doing log base 2 of x and then the 3 separate. But because x plus 3 was on the side first before applying the log base 2, I need to apply it to the entire side. That's why I put parentheses. Does that make sense? So the log base 2 of 2, this guy right here cancels out. Y comes down. Y equals this stuff. So y equals log base 2 of x plus 3. And right there, because it's in parentheses, technically that's an H shift, not a K shift. Okay? So we've done several examples on how to find the inverse applying logarithms or raising both sides to be powers of whatever base we need. Let's flip the paper over and let's do some graphing of logarithms. So right here I'm explaining that it could be very confusing to try to do the xy table of a logarithm function. Y equals log base 3 of x. That's this guy up here. And if I actually tried to do an xy table, it's really difficult. Like, you can't even plug in 0. Why not? Think about it. If I put a 0 right here, we're really thinking 3 to what power gives us 0 as an answer, and that doesn't work. So it's really hard to do inputs and outputs when you're thinking of a logarithm. So it's better to just think of the inverse of that logarithm that has no h or k. So you think of the inverse of it by looking at the inverse, which is y equals 3 to the x, and actually graphing y equals 3 to the x, and then switching those coordinates to get the actual coordinates of the logarithm function. After all, an inverse is really switching x and y, so if you're able to find the coordinates of the exponential growth function, then the coordinates of its inverse would be simply switching the x and the y values of the coordinates. I hope that makes sense. I know it's a lot of words, but so let's do this one. Let's graph. We're going to graph y equals 3 to the x. Let's use consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3. Let's plug in the easiest one, 0. When I plug in 0 into the exponential growth function, which is the inverse of this guy, 0 right here, anything to the 0 power is 1. And you could use the growth function to make the outputs grow. So 1 times 3 is 3, times 3 is 9, times 3 is off the graph. Going backwards, it would be not multiplying by 3, but multiplying by the reciprocal of 3, which is 1/3. So 9 times 1/3 is 3, 3 times 1/3 is 1, 1 times 1/3 is 1/3, 1/3 times 1/3 is 1/9, and then 1/27, which is ridiculously small. Now, the actual coordinates of my logarithmic function will be these coordinates, but just switching x and y, because this guy is really the inverse of this guy. And inverses, we know to find the inverse, we switch x and y. So let's just simply switch these x and y's to get the actual coordinates of our logarithmic function, log base 3 of x. So the first coordinate, instead of -3 and 1/27, I'm going to say 1/27 and -3. Instead of -2 and 1/9, I'm going to say 1/9 and -2. Instead of -1 and 1/3, we say 1/3 and -1. Instead of 0, 1, 1, 0. Instead of 1, 3, 3, 1. Instead of 2, 9, 9, 2. And the other one's off the graph. So let's graph our actual logarithmic function. Let's begin with the easiest coordinate, 9, 2. 9 on the x, 2 on the y. Here it is. Let's go with 3, 1. 3 on the x, 1 on the y. There it is. Let's go to the next one, 1, 0. That one's pretty easy. 1 on the x, 0 on the y. There it is. And then 1/3 -1. This is where it gets a little weird. 1/3 is not even halfway out. It's just 1/3 of the way out and then -1. So we're going to put a dot right there. It's pretty close to the y-axis. Now the next one, 1/9, it's even smaller. It's even closer to the y-axis. 1/9 is super close to the origin, and -2 is down here, so it's even closer to the y-axis. Does that make sense? So as we're going this way, it's getting closer and closer and closer, infinitely closer, but we know it never actually touches. It just infinitely approaches, which means that our asymptote is the y-axis itself, the x equals 0 line. That's our asymptote, x equals 0 line. So this is our graph for our exponential, oh no, this is not an exponential, this is a logarithmic function. For our logarithmic function, log base 3 of x. Now, what if we were to have graphed the exponential growth function, which is the inverse of it? What would happen? Let's just show it real quick, just so you could visually see the difference between the inverse functions. If I were to graph let me do this one in blue, 0, 1, that would be right here. If I graph 1, 3, 1, 3 is right here. If I graph 2, 9, 1, 2, 9, it's up here. And then 1/3, and then 1/9, 1/27, and so on and so on and so on. Here's my asymptote. So what do you notice about the red graph compared to its inverse, the blue graph? It's a reflection. It's the same exact graph. It's a reflection over this line right here. And what is that line? That line right there is the y equals x line. And that makes total sense. Because if y equals x, it doesn't matter if you switch them, right? Which is what we do on inverses. We switch x and y, then solve for y. So that's a pretty cool truth, that when you graph exponential growth function and then you graph its inverse, it really is a reflection over the y equals x line, which makes total sense because when you do find the inverse, you switch x and y in the first place. So let's graph, how about, I don't know. You guys want to do this one? That actually has an h and k shift? Okay, let's do it. What is your h value? What's your k value? Okay, so once you identify h and k, just like always, ignore h and k, box in your function. We'll call this our parent graph function. Now, if I wanted to graph this guy, log base 2 of x, it's really complicated to start thinking of inputs and outputs right there. So what I'm going to do is get the coordinates of the inverse by ignoring log. It's going to look like y equals 2 to the x. And that right there, y equals 2 to the x, is a pretty easy problem to graph. It's an exponential growth function. I want to make some inputs and outputs, consecutive integer inputs. Let's plug in the 0. It's the easiest one because anything to the 0 power is 1. So you get a 1 as your output. And then we're going to make it grow by that growth factor of 2. 1 times 2 is 2. Times 2 is 4. Times 2 is 8. Going backwards, it would not be multiplying by 2. It's actually multiplying by the reciprocal of 2, which is multiplying by half. 8 times half is 4. Times half is 2. Times half is 1. Times half is 1/2, times half is 1/4, times half is 1/8, and we know it keeps getting smaller and smaller and smaller by half. Now, I am not going to graph this guy this time. I mean, if you wanted to see that it's a reflection over the y equals x, that's fine. But the only purpose of me actually getting the coordinates of this exponential growth function, which is really the reciprocal of y equals, not the reciprocal, which is really the inverse function of y equals log base 2 of x, is to get these x and y values so I could switch them to get the actual coordinates of y equals log base 2 of x. So my actual coordinates will be, for that boxed in function, will be 1/8 and -3. It'll be 1/4 and -2. It'll be 1/2 and -1. It's going to be 1 and 0. Hi. 2, 1. 4, 2, and 8, 3. So let's graph this. Begin with the easiest coordinate, not this first one, 1/8 and -3. It's easier to graph 8, 3. So graph 8, 3, 8 on the x, 3 on the y. 1, 2, 3, here it is. 4, 2, 1, 2, 3, 4 on the x, 2 on the y, there it is. 2, 1, 2 on the x, 1 on the y, there it is. 1, 0, 1 on the x, 0 on the y. And then for the harder ones, 1/2 -1, that's halfway out on the x, -1 on the y. So we should by now already understand that it's going to get closer and closer and closer to the y-axis this time, which is our asymptote of this boxed in function. It's not our actual asymptote because we still need to shift all these coordinates where? 3 to the left and 1 up, according to our h and k. All right, so we need to shift all of them 3 to the left and 1 up. Now, what does this mean? What will my asymptote actually be on this guy? What's my asymptote actually on this guy right here? It is -3. X equals -3. Think about it. Right here's our asymptote right now, but if I shift all of them 3 to the left, my asymptote will be right here. So we could actually draw that asymptote if we want at the x equals -3 line. And you could shift all these coordinates 3 to the left and 1 up. So if I go 3 to the left, 1, 2, 3 to the left, 1 up, put this in blue, and then shift all of them 3 to the left and 1 up. Wait, I didn't do that right. I'm sorry. Technical issues. So there we are. Every point shifted 3 over and 1 up. So this blue graph is our logarithmic function graph. Let's throw in some more info on this graph. What's the domain of the blue graph? X is greater than the h value, -3. Why? Because this whole blue graph is on the right side of the x equals 3. It's on the right side. It never actually touches. Even though I draw it like it does touch, it never actually touches. And how about the range of this blue graph? Y definitely is all real numbers because it does go down forever on the y's and it does go up forever on the y's. Even though it curves this way, it continues to go up forever. So it goes up and down forever. So your y values are all real numbers for your range. Okay, so you guys can handle this one, right? You're going to graph the function y equals, it's a decay function, 1/3 to the power of x, and then switch your x and y values and you'll have your graph.